Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to derive the formula to construct a confidence interval for sigma squared, the variance, under the assumption that we have a sample from a normal distribution. Okay? Let's begin. So, as I said, that's what we're going to be doing here. We're going to be constructing a confidence interval for sigma squared. And also, as I said, let me remind you about our assumption. We have n observations coming from a normally distributed random variable. Okay, so these guys are IID, independent and identically distributed. Okay, we have n of them. So normal with mean mu and a common variance sigma squared. Okay, so now let me remind you, right? We talked about this theorem 7.3, right? So we know from theorem 7.3 that given that assumption that we have these guys and they are independent and identically distributed, the following quantity n, not what I wanted, n minus 1 times s squared, where s squared represents the sample variance, right, divided by sigma squared, that quantity, that statistic, has a chi-square distribution with n minus 1 degrees of freedom. Right? Okay. So, just for fun, well, not just for fun, but maybe I should remind you about the formula of s squared, right? S squared is 1 over n minus 1 times summation of I goes from 1 up to n of yi minus y bar squared. Okay, make sense? Okay, so now let me make an observation here. Let me point something out. That note that this quantity, n minus 1 times s squared divided by sigma squared, is a function where the only unknown is sigma squared, right? N is the sample size, so we know it. S squared, from our sample, we can compute that guy, right? So this is a function where the only unknown is sigma squared, and on top of that, right, the distribution of that function is independent of sigma squared. So this guy is a pivotal quantity. So let's write that down. Note that this guy is a pivotal quantity. So we have encountered and used those before, right? So we know that a confidence interval looks something like this, right? What we're going to have here, what we want to find here is two numbers. Let me call this guy chi-square sub L and chi-square sub U. Oh, not what I wanted. I want this. That's better. Okay, so chi-square sub L and chi-square sub U. That's going to be the other one. And they represent the lower and upper limits. We would like to find these two numbers that satisfy the following restriction, if you will, right? We want them to satisfy this property that between these two numbers we have a probability of 1 minus alpha, right? We want to have that confidence level, we call it, right? So to make things a bit clearer, right? Let me show you a graph. That's what we need, right? We need those guys to satisfy this, right? Between chi-square sub L and chi-square sub U, we want to have that proportion of observations, 1 minus alpha. That would be our confidence level, okay? So, well, one thing that we can do, right, is we could just do a little bit of algebra. Note that one way of proposing, well, one possible value for these guys would be chi-square sub L would satisfy that the area to its left is alpha divided by 2 and chi-square sub U is alpha divided by 2, right? You could propose something different, right? Note that for instance, you could have 1 minus alpha, right? If you started from 0 and you reached a point where the area to the left is 1 minus alpha, right? But that is not what we want, okay? So anyway, we are going to find chi-square sub L and chi-square sub U using that idea of having an area of alpha divided by 2 to the left of chi-square sub L and an area of alpha divided by 2 to the right of chi-square sub U, okay? Okay, so let's do that. So now we are going to kind of switch notation here, right? And I want you to see something else, so the notation that I'm going to use makes sense to you. So we're going to be using table 6 from our textbook. So you'll find it on page 850 of our textbook. Note that that alpha that we have here refers to the area of the right tail, meaning the area to the right of quantile, okay, not to the left, okay? So, going back to our graph, the area to the right of chi-square sub L would be 1 minus alpha divided by 2. Makes sense? To the right, we have all this. So to the right, what we have is 1 minus the area to the left. And then to the right of this guy, clearly the area to the right is just alpha divided by 2. Makes sense? And we're going to be using that notation to make it match with the graph that you have here on table 6. Make sense? So here we go. Again, to the right of chi-square sub L, we have 1 minus alpha divided by 2 to the right. And to the right of chi-square sub U, we have alpha divided by 2. So we have 1 minus alpha divided by 2. And here we have an area of alpha divided by 2 to the right of this guy. Make sense? Okay. Now, solving for sigma squared. So note, right? So let me do this with this guy here. So we multiply by sigma squared on both sides, so we end up with this, right? If we multiply this first inequality by sigma squared, right? Then if we divide by this guy on both sides, we end up with this. Make sense? Okay. Now, that's one side. Now let's take into account this guy here. The other inequality. Doing the same, multiplying by sigma square on both sides, I have this. But then I divide by chi-square sub alpha divided by 2, and I end up with this. Now, if we, paste these two inequalities, what we have is that that sigma squared is greater than n minus 1 times s squared divided by chi-square sub alpha divided by 2, and sigma squared is going to be less than n minus 1 times s squared divided by chi-square sub 1 minus alpha divided by 2. Make sense? So I'm going to combine these two inequalities. So if you will, let's just leave these here as rough work. And then below, we're going to paste them, right? So first, this one. Now this one. But that event is equivalent to what we had here, right? We just solved for sigma squared. So the probability of that event is going to be 1 minus alpha by construction, right? Make sense? Okay. So now I want you to see that what you have here, these guys here, right, form a 1 minus alpha confidence interval for sigma squared, right? We can find these guys, right, s squared, we can find from the information contained in our sample. This is the sample size. These guys here are quantiles, right, are critical values from chi-square, right, with n minus 1 degrees of freedom, and with, in this case, this one here with an area of alpha divided by 2 to its right, this one with an area of 1 minus alpha divided by 2 to its right. So we can find those guys with a table, for instance. So we're basically done. So now let me show you that formula here, right? That's exactly what we did. And again, that slide summarizes well, the formula that we're going to be using to find a confidence interval for a variance, right? Now, really important, and you saw that from the derivation, right, that we did together, that the assumption that those observations come from a normal is really important, because then we get to use that theorem 7.3 that tells us that the distribution of n minus 1 times s squared divided by sigma squared is chi-square with n minus 1 degrees of freedom. Okay, and now again this notation should make sense, and again we are using this notation because we're going to be using that table. So this guy is a critical value from a chi-square with n minus 1 degrees of freedom, such that the area to the right is alpha divided by 2. On the other hand, this guy here is, yeah, a critical value from a chi-square with n minus 1 degrees of freedom, but with an area of 1 minus alpha divided by 2 to its right. Okay, but we can find both using a table like this one, right, or using R. We're going to be doing an example where we test drive, if you will, our formula. But for the time being, we're done deriving that formula. We'll use it later. Okay? Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.